Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to find the velocity and acceleration of one object with respect to another. So what we're looking at here is we got a pair of vehicles. Vehicle B here is moving at 10 meters per second and has a tangential acceleration of 2 meters per second squared. Vehicle A here is moving at 5 meters per second, and we'll assume that to be constant in this example. And what we're going to try to calculate here is the velocity of car B, the velocity and acceleration of car B as seen from a passenger in car A. So let's start with the velocity. The velocity of car B with respect to A is equal to the velocity of B minus the velocity of A. So it boils down to trying to find these guys, velocity B and velocity of A. Velocity A is no problem at all. Velocity A is moving, or car A is moving 5 meters per second down, so that's going to be 5 in the minus j. I'm going to go ahead and just put the units out here. And that's it, there's nothing to that. All right, car B, however, we've got to do a little tiny bit of work. The velocity vector for car B is 10 meters per second, and it makes some sort of angle here with the horizontal. So if I were to draw like a horizontal dashed line here, we start looking at the angles. This is a 60 right here. That makes this one 60. That makes this interior angle 30 degrees. This 10 meters per second can be broken into x and y components. The x component would be adjacent to the angle 30 degrees, and the y component is opposite the 30 degree angle. Therefore, the velocity vector for B is equal to minus 10 cosine 30 I plus 10 sine 30 j. I'm going to go ahead and just put the units out here, meter per second. So the velocity of B with respect to A is given by this vector minus this vector. So by subtracting components, we're going to have minus 10 cosine 30. Now you'll notice that velocity A doesn't have an x component, so I guess I'll just put minus 0 I plus, now we're going to take the difference of the y coordinates. We're going to have 10 sine 30 minus a minus 5 meters per second. So we're going to have 10 sine 30 minus negative 5, and I'll go ahead and put j out here. And let's put some units on that, meter per second. So it's pretty easy to calculate this. Minus 10 cosine 30. Let's see, that's equal to minus 8.66 I plus, and when we do, let's see, 10 sine 30 is 5, minus a minus 5 is plus 10 j. And again, these are in units of meter over seconds. So there's the velocity of B with respect to A. We've got the velocity vector. If we wanted to know the magnitude of that vector, we could Pythagorean theorem apply to it. We will, like Yoda would say. And that would give us the rate that this distance is changing. All right, we'll start working on the acceleration vector. I'm going to clear myself off some space because I'm going to need it. So we're not going to need this stuff anymore. All right. So now we're going to work on acceleration of B with respect to A. So acceleration of B with respect to A is going to be given by acceleration B minus acceleration A. I'm going to do the easy one first, acceleration A. Now, when we look at car A, its velocity vector points straight down, but we need to recognize there's a centripetal acceleration that points to the right. So I'm going to go ahead and draw that vector on car A, and I'm going to draw my acceleration vectors in red. So car A has a centripetal acceleration that points inward. That acceleration has a magnitude of v squared over r. That's going to be 5 squared over 70 in units of meter per second squared, and that comes out to be 0.357. All right, while I'm at it, I'm going to go ahead and calculate the centripetal acceleration of car B, because car B is also moving in a circular motion type of path. So I'm going to draw it first and then calculate it. So remember, centripetal accelerations always point towards the center of curvature. So the centripetal acceleration of B points inward. I'm not going to worry about the relative magnitude just yet. All right, that vector will have a magnitude v squared over r, so that's going to be 10 squared over 70. The units are consistent. I'm going to leave them out. And I get 1.43 out of that. 1.43 meter per second squared. And it's important to note that that vector makes an angle of 60 degrees here with the horizontal. Now, in addition to the 1.43 meter per second squared, car B also has a tangential acceleration. The tangential acceleration is in the same direction as the velocity. I'm going to draw it in red. And that vector has a magnitude of 2 meter per second squared. So we have 3 acceleration vectors to worry about. I'm going to go ahead and write out the easy one here, which is acceleration of car A. The acceleration of car A is 0.357 I, and those are in units of meter per second squared. And that's done. All right, B has a little more going on. The acceleration of car B is the vector sum of the tangential and centripetal acceleration vectors. So that's going to be minus 10 cosine 30 minus 1.43 cosine 60 I. Let me talk about where I'm getting that from. So, whoops, and I got to back up, not 10. Got to be careful about that. That was a velocity vector. I got to go back. I'm going to go ahead and leave this in the video here just to make a point. You got to be very careful. I got different types of vectors on the board here. So this 10 meter per second was for the velocity of car B. The acceleration vector is the red one, and that has a magnitude of 2 meter per second squared. So that's going to be minus 2 cosine 30. So this vector has a magnitude of 2. Its x component is adjacent to the 30-degree angle, and it points to the left. That's why the minus 2 cosine 30. The centripetal acceleration has a magnitude of 1.43. It makes an angle of 60 degrees with the horizontal, and it also points left. That's where I'm getting the minus 1.43 cosine 60. I'm going to go ahead and do the y components, and I'll just tack units onto the end of this thing. All right, y components now. The y component of the tangential acceleration vector is opposite the 30, so it's going to be 2 sine 30, and it's positive. This guy's y component is here, opposite the 60-degree angle, and note that it points down, so it's going to be minus 1.43 sine 60 degrees. And there's our direction, J, and now I get the units on this whole thing. Meter over second squared applied to all of it. All right, so I think what I'm going to do here is simplify this down a bit before I move on. So acceleration B, if I just take a calculator and run a value for this, I get minus 2.45 I. And that's just coming from minus 2 cosine 30 minus 1.43 cosine 60. And then when we run 2 sine 30 minus 1.43 sine 60, I get minus 0.238 J. And again, those are in units of meter per second squared. All right, so we're ready, just about done here. So the acceleration of B with respect to A is going to be acceleration of B minus acceleration of A. So that's going to be minus 2.45. All right, this x component minus this, minus 0.357 I, and that'll be in units of meter per second squared. I'll go ahead and tack that on at the end, plus, right, acceleration vector B, J component, minus 0.238, minus the J component of A's acceleration vector, but A doesn't have an acceleration vector there, so I'll just put minus 0 J, and this is all in units of meter over second squared. And one more line here. So what I get after it's all said and done here is I get minus 2.8I minus 0.24 J in units of meter over second squared for the acceleration of B with respect to A. I went ahead from this line to this line, and I decided to round to 2 sig figs. We could Pythagorean theorem this if we wanted to, but there's really no reason to. I think it's a pretty acceptable answer just the way it is. I hope this video helped demonstrate how to find the acceleration of one particle with respect to another. Have a great day.